Hey guys, Mr. Betts here. I'd like to take a look at one more method that we can use for evaluating limits. This method, the squeeze theorem, is going to be something we can use when a lot of the other methods that we've tried don't work. So if you remember in the last section, we looked at this flowchart here, and in particular, when we're dealing with indeterminate limits, we tried using factoring and conjugates and trig identities. And if those things didn't work, we said, okay, let's try a numerical approach. We'll try approximation. Well, approximation is really kind of limited in its precision. We can get an idea of what a limit might be, but it's not a very rigorous method. So the squeeze theorem is going to give us a more rigorous method for evaluating some limits where these other options don't work. So let's start with just the formal definition of the squeeze theorem, which says this. So I want to start at the end here and kind of get an idea of what we're trying to do with it. And the idea is we're trying to evaluate a limit for some function that I'm going to call f of x here. And so we're trying to evaluate a limit as x approaches some particular constant, just called c here, of f of x. And we're going to use two other functions to help us do that. And so the f of x function is going to be squeezed between the other two. So in order to use the squeeze theorem, this inequality has to hold. All right, so I do want to point out that it doesn't matter what's happening at x equals c. And you should remember that with limits before. We don't care what happens at x equals c. All we care about is what's happening around x equals c. So when it says in some interval about c, that's just saying in the neighborhood. So somewhere around it. It doesn't have to be for all values of x. And so if we have some function that's always smaller than or equal to f, and another function that's always bigger than or equal to f, and the second part here is really important, those two functions approach the same value, so their limits at c are the same thing, then that means that f is going to be squeezed between them, and since they have the same value, then f will also approach that same value. All right, so graphically, that's going to look like this. So we have this function that's bounding f above. We have a function that's bounding f from below. So f is always going to be somewhere in between those two. And you can see in this picture here, the upper function and the lower function are both approaching the same value. And so we know that f also has to approach that as long as this inequality holds. All right, so it's a pretty simple idea. I do want to point out that this part right here where it says for some interval about c means that we could have a function f that does go outside of the interval at points. So it could go above the upper or below the lower, as long as in the neighborhood around where we're looking, around c, this inequality always holds. So I'm gonna do a couple examples in another video. One in particular for a special limit that's one that we can't evaluate using numerical methods. We can't evaluate using algebraic methods, and the squeeze theorem is going to be able to work for us.